Our keynote speaker received the PhD degree in computer science from Uppsala University, Sweden in 2002. He is currently a professor of computer science with the Department of Electrical Engineering, Uppsala University. He also leads the Networked Embedded Systems Group, Research Institutes of Sweden, Computer Science, Stockholm, Sweden. His work has been cited more than 17,300 times. His current research interests include low-power networking, system software for embedded network devices, and Internet of Things. He is also a member of the editorial board for the IEEE IoT newsletter and ACM transactions on sensor networks. Speaking of towards in-body, battery-free Internet of Things, ladies and gentlemen, it is my pleasure to invite Professor Thiemo Voigt. Professor, the stage is all yours.
So let's wait until the slides pop up. So thank you very much for this intro. This was one of the very first time that somebody pronounced my name correctly. So great job. Okay, it's here. So yeah, welcome to my talk. I'm very happy to be here and present this keynote. And before I start, I want to say thanks to everybody who has invited me and for all the kind help I got during this day. So what I'm going to present is a bit about the journey of we've been doing in the last 5 years. So we've been working a lot on in-body sensor networks. We've also been working a lot on trying to make the IoT battery-free. And what I want to present in this talk is both these technologies and also how we in the future actually are thinking of combining these two technologies. Before I start, I want to say a few words about myself. So I have a PhD in computer science, which was already said by the intro. I was working on overloaded web servers during that time. This is more than 20 years back. Since then, I've been doing a lot of low-power networking. How can we connect really small embedded systems wirelessly in a smart way? We've been doing a lot of systems research and a lot of open source, actually. So an operating system for the Internet of Things called Contiki is one of the main outcomes from what we've been doing in the last 20 years. So this is a little bit longer back. So this operating system work started in like 2003, but there are still many universities and companies using this. I collaborate with lots of different people from computer architecture, from human-computer interaction, electrical engineering, and in particular, my main collaborator these days is a person called Robin Augustin, and he works a lot on biomedical microwave engineering. I also work a bit with industry because at Rice we are a little bit closer to industry than at university. And I've been doing a lot of work with the people here. So Kasun, Shamat, Asanka, Chatara, and many others, we have had joint projects since roughly 10 years back. So one of our first funded project was that we're starting on localizing elephants. Well, it seems like it's an easy task because they are quite big, but you also want to identify them when they are further away. So this was a very exciting project. Then we thought that elephants are pretty big. Let's get to smaller animals. So since 2 or 3 years, we're running a project on fighting dengue fever with drones. This is about trying to find out where actually mosquito larvae are breeding, and using drones and some like machine learning also to detect where we have mosquito breeding sites. Great, but let's start into this in-body sensor networks. So already many years back in 2005, there were 25 million people in the US that had implants. Most of these implants were actually pacemakers, but we think that the number of implants that people have and the number of people having implants, this will only increase and will become more and more. Because people are getting older, they have more and more diseases. The implants will also getting better. There will be more and more implants coming. So for example, there will be drug delivery system, there will be artificial organs. People talk a lot about kidneys, they seem to be simple, maybe that's why. We have also worked on, implants to measure measure pressure within the skull. And if you have several implants in your body, it makes also sense to network these devices. Oi, this was not supposed to go that fast. Let me go back a little bit. Right, I should be closer, I was told. Oh, I was really, really fast. Right, I was here. Wait, so this is the next one. Right. So we said that we should network these implants, and there are existing methods for doing it. There is galvanic coupling, and there is capacitive coupling. But these methods, they provide very low data rates only. We're talking about some kilobit or something per second. So what my colleague Robin has come up with, and which we've been working on, is to use normal radio frequency communication within your body. That could be something like Bluetooth, for example, or it could be Zigbee that some people know. We have also tried Wi-Fi, right? So you could have Wi-Fi in your body. I talk a little bit about this more. But you cannot just send it everywhere. It turned out that the fat that we have in our body, there's a lot of fat under the skin. For example, there's also fat around the organs that we have inside our body to protect the organs. Fat is everywhere within the body. And it turns out that, yeah, normal Bluetooth, Zigbee communication actually works well through the human fat, which is an amazing insight that Robin actually got. And here you can see two pictures. The white stuff that you see here is the fat, and you can see here fat is actually, well, in many places inside the body. Let me change that. Okay. And I want to make one more argument why networking the devices inside the body is actually interesting. There are some places inside your body where it's difficult to couple signals in and out. And you want to couple signals out so that you can read some data values. And you may want to couple signals into the body so that you can, for example, reprogram or retask something in your body. And if you're now at a place where it's difficult to get out a signal, you may use a repeater. Send the data to another place in your body and then do a multi-hop communication and send it from this repeater to an aggregator. And the aggregator is basically the gateway between inside the body and the outside world. And this communication within the body actually works quite well because the fat is typically situated between skin and muscle. And it works very well to communicate within the fat, but it doesn't work very well to communicate through skin and muscle. So these act as a kind of waveguide, which means that the radio waves bounce around within the fat, between the skin and the muscles, but they don't go out through the skin and the muscle. Well, through the skin they could go out, right? But the attenuation through the skin is very, very large. So only a very little fraction of the signals actually go out through the skin. I will come back to this a little bit later. Right here we can see why this is the case. So here in this table we have we show the relative permittivity of fat and muscle, and you can see that in the fat also for different frequency this is much lower, right? And lower permittivity means that it behaves similar to air, where radio frequencies, they travel very well, as it is known. So this is kind of this is why communication with radio frequency waves in the human body actually works quite well. So when we started to see if this works, so we used lots of different methods to show this. So we were using simulations with a simulation tool called CST, but we were also using something called ex vivo. This means more or less we went to the butcher and we bought meat, fat, and we're sending our radio frequencies through this fat, through this animal fat. And then we also built something called phantoms, and phantoms are artificial, they are kind of artifacts that mimic the behavior of human tissue, right? You cannot just take humans and put in some implants and send something through them. So what we're doing instead is that we're trying to devise artificial entities that have the same properties as human tissues. So these are these phantoms, right? So here's, you see on the left hand or on the right hand side from you, you see a very simple phantom where we have the skin, the fat, and the muscle, right? So here you can see that the fat is, between skin and muscle, which act as the waveguide. But we have also done some very complex phantoms. So you can see here the torso, meaning this part of a human body. So there are some internal organs that are modeled. The skin and the fat are modeled. So this is we were actually building two different versions of this. This is the athletic versions. There is not so much white stuff, meaning fat, but we also have an obese version where there is much more fat. Here are some results. These are some results from phantoms. So what you see on the x-axis is there you can see the different frequency, the different radio frequencies. 2.4 is where you have, for example, the older versions of Wi-Fi and where you have Bluetooth. And on the y-axis, we see the S21. So this is basically how well the signal goes, right? And you'll be doing this for different lengths of the phantoms that we have. And you can see from the results that, the received signals are actually quite strong. And what you can also extract is that what is on the right-hand side, the attenuation is roughly 1 dB per centimeter. And this is not very much, say it in simple terms. So these are results with phantoms. Then we also did this, as I said, with ex vivo, meaning with meat that we bought. Again, you can see the frequency on the x-axis, and you can see the received signal strength on the y-axis. And in this experiment, you see that the received signal strength is a little bit lower. And here, the attenuation is roughly 2 dB per centimeter, which is still low. And probably the true value is somewhere in the middle between these two values. So this was, in these first experiments, we were not really sending any data packets or something, but we were just doing measurements. So here we have a setup where we have a software-defined radio. Then on the right-hand side, you see probe means an antenna. So you can match what you see in these schematics down there to what you see above. So the probes are the antennas. Then there is the phantom itself with skin, fat, and muscle. And we were sending data packets through this. And the results you can see on the next slide. So on the x-axis, you have the distance, how far we send this, the distance between these two antennas, the transmitting and the receiving antenna. On the y-axis, you have the received signal strength. And as you can see, that is very obvious, and that's how it should be, that the farther you travel, the lower the signal strength becomes at the receiver. And here, the attenuation is roughly a bit between 1 and 2 dB per centimeter. Right, so now we have said that we have a medium, the fat within the body, through which we can send data, right? So we have a communication channel within the human body that allows us to send signals from one place within the body to another place in the body. But we can actually do more than that. We can also use this channel for sensing. What you see here now in this, you have like this perturband. So in the fat layer, there is now a kind of a hinder growing. And this could be, for example, a tumor, a cancer tumor that is growing. And when you have this tumor growing, it turns out that the received signal strength decreases, right? Which is kind of obvious. There is a hinder. This means more radio waves are bouncing against this hinder, and because of this, may escape out through the skin. So here in this graph on the x-axis, we see the size of this perturband, which could be a cancer cell. And on the y-axis, we see the received signal strength. And we can see that if this tumor starts to grow, then the received signal strength decreases. So this means, as I said, we can use this channel not only for communication, we can also use it for sensing. And one of the applications of this is tumor relapse, right? So for example, breast tumor, right? So what we have modeled here, so you can see here in the middle of the screen, you see this is a phantom of a human breast. And on here we have some experiments, right? We're setting up the antennas, we're doing the measurements, And what we saw on the graph on the previous slide, again, as the diameter of the tumor increases, then the received signal strength decreases. So this is very, very personal data, right? So this is something that we don't want to expose to everyone, right? So that we've put in quite some work in order to make this privacy preserving, meaning that even external attackers who are, for example, sitting on the skin may not be able to defer that there is a tumor growing, because they may not be able to infer that the signal strength decreases. Right? This sounds very simple, right? You just vary the output power of your radio, of the transmitter, but it turns out that this is not really sufficient, right? Just doing it, just varying the output power, and by this, it impacting the received signal strength is not sufficient, because you may have one attacker before the tumor and one after the tumor. So it turned out it became actually kind of complex to do that. But we found a solution. Right, so I showed you now some of the results from our journey to show that this RF communication within the body is actually possible. We have some more results. We have, for example, shown that you can communicate from the front to the back. Well, this was the wrong direction, from the front to the back. This, with Bluetooth, this works, for example, inside, but typically the radio waves bounce away, and then they need to reflect somewhere to come back. And if you're now outside, then with Bluetooth, for example, this may not work very well. We also looked at the impact of blood vessels, right? They could also hamper the communication, just like the tumor does. We have also looked at what happens if this fat is not really, really straight, but if there are some bumps, if it's concave or convex. This also turned out to work. And also the antennas, the probe, they might be not well aligned, but they may get a little bit shifted and out of focus. This also has an impact, but it's not that big. We have tested different frequencies, like 5 gigahertz, which is where most of the Wi-Fi is operating today. This also works, but the big advantage is the antennas can become a little bit smaller, but then we also lose a little bit of the distance, the maximum distance we can bridge. Right, so on the next slide, I'm discussing a little bit there now. We have this aggregator, we have the gateway between the outside world and the network inside the body. And this aggregator, there are different ways of doing it. You can have a totally implanted aggregator, or right, you can have it first outside, right? You can have an aggregator outside and then try to launch the signals through the skin. This works, but you're losing something when you go through the skin. You could have it partially implanted, like you have some kind of a needle that goes through the skin. This is like commercial glucose monitoring works. And we could also have a variable with an in-body repeater, meaning you have the aggregator just outside and have another implant just close to it. Then you can also communicate between two. But which this is the best solution depends really on the application that you are doing. Great, so let me now summarize about this, using the human tissue, the human fat tissue for in-body communication. So this is a low-loss channel. We get a pretty high bandwidth. There is not so much impact from disturbances, but enough that you can use it for example, tumor measurements. So from this point of view, this is a useful and efficient channel within the body. We've done lots of more work in this specific area. So we've done some privacy-preserving techniques for these tumor measurements. We've also done some work, and this is something we are taking up at the moment again, something like covert communication, where we're actually trying to hide that there is some communication going on in the body anyway. So one of the means of doing this is that the aggregator, this device that you have outside, sends some radio waves to confuse some people who want to figure out if there is some communication going on inside the body. We also looked at this is some security work, how you can actually do authentication and key agreement based on entropy that is found inside the body. We have shown that we can handle malicious devices on the body with this and in the body. So previous approaching could not do that. They assumed that everything that was in or on the body was actually not malicious. We have worked on antennas to restrict the leakage. We have worked on in-body control loops and on physical layer attack detection by using fingerprinting, which is an interesting technology. And we've worked on making this aggregator also secured. And one of the most recent works was some secure multipath routing within the human body. So let me get to one of these new works. So this was actually done by Padmal, or he was the main contributor. Padmal is a PhD student from this country, right? I also have one current patient from Sri Lanka, and one defended just his PhD student a while ago. So I'm very happy, thanks to the connection with UCSC. I had some really great PhD students. So what these other communication technologies always claim, if you look into galvanic and capacitive coupling, they always claim that this RF communication is not useful because it leaks. And as we know, it leaks, but nobody really knew how much does it actually leak. So here we've been working on trying to figure out how much does RF leak and if you can do something about it. So this sounds very easy, right? You build these phantoms, as we said, and that I talked about, and then you do some measurement and you get the results. But the problem is that RF is really, really tricky. Wherever it can escape, it escapes, right? So where you put in the antennas, they escape very close to that. We also have to admit that we had a little bit of problems of modeling the FET. It did not communicate as well as it should. But finally, in the beginning of this year, we actually got some very, very nice result. So what we did here, we have a phantom that we shielded. We shielded on the bottom and to the right and the left, so that radio frequency waves could not escape. Then we put up a transmitter that you can see here. This is the transmitter, but the antenna is put somewhere inside of here. We have the receiver here with the antenna put here, and we have some eavesdroppers. Those are those interested in eavesdropping on the communication that happens. So this is a kind of interesting setup, and this finally turned out to work. So I have some results that you can see here. So what we have is the diagram on the top right. We have a transmitter. Then we have 4 receivers, 4 eavesdroppers, E4, E3, E2, E1. E4 is the one closer to the transmitter, E1, the one farthest away from the transmitter, and we have a receiver. Here on the y-axis, you can see the transmission power of the transmitter. So the more to the right, the higher the transmission power. And on the y-axis, we have the received signal strength in dBm. And what we would expect, of course, if we send with a higher output power, then we get stronger signals on the other side. And of course, then the eavesdroppers that it's further away should get the lowest signal strength, right? And you can see this, the blue line is the lowest line, and you can see among the lines in the lower one, the red that is the closest has the highest transmit power. But you can also see that the receiver that is inside, this is the purple line, this is the one who receives the highest, who has the highest received powers. And this is caused by the signal attenuation through the skin that these eavesdroppers get. And from these results, it's not so easy to see, but you can see that the loss is 27 dB when we're going through the skin. So this is a very, very large attenuation. But this means that some signals leak out, but there is a high attenuation when they leak out through the skin. So here we have again a similar setup. Now we're looking into how many packets we receive. So on the x-axis, we have the output power of the transmitter, and on the y-axis we have the received packets, so the percentage of the received packets. And what we see on the left-hand side, if we're working with a kind of higher output power, well, it's not very high, it's very, very low compared to Wi-Fi or your mobile phone. So it's minus 30 dBm. What we can see here that, everybody receives all of the signals. Well, the blue node that is first away, the blue eavesdropper has some problems. But you can see when the signal strength is, low enough, then it's only the receiver inside the fat channel that still receives any packets, whereas the other ones do not receive anything if you're working on a very low output power. So what does this mean? This means actually that if we are choosing our output power low enough, then only the receiver inside the body can receive packets, but the other receivers cannot. However, this assumes that we have receivers or eavesdroppers that have the same capability as the nodes inside the network. Oh, sorry, I was again here a little bit too fast. Great. Okay, so now we have said, we're having these implants, we can communicate with these implants, but what can we actually do, right? So we can actually do some very cool stuff with this. For example, if we think about prosthesis, we could actually control from a brain-machine interface through the fat, through the arm, we could control a bionic arm, right? And this is something we are working on, and this is something which is very useful because we are avoiding cables, and we can also make use of the high data rate that you need if you want to control and have many degrees of freedom for the prosthetic arm. And here's kind of an illustration of this. So we would have a brain-machine interface somewhere here on the back, right? There are implants that exist, right? So we could use this. We could then communicate through the fat to control and to actually control the bionic arm. We can even do more. We have a person who works on kind of trying to create electronic skin that knows how hard is it touching something. And this would enable a control loop between the brain and the prosthesis, something that is actually lacking today. Something else that we could do is exoskeletons. So exoskeletons also need lots of degrees of freedom, and that's why we also need to send a lot of data. If you want to do this, right, then you need to have lots of cables, which increases the weight. So it's actually a very interesting idea to send the data as packets through the fat, and by this way control these exoskeletons. I thought this was not so super duper useful, but then I actually met a person who worked on exoskeletons, and he said, this is really, really a great idea, and we need to try this. So I was very happy to hear that actually other people think that this is useful. Another application area, so this is something that my colleague Robin's brother called Bobbins works on. This is actually vascular robotics. So there's a lot of things going on in robotic and surgery, right? For example, here is a Da Vinci robotic system. This is really, really expensive, but it's of course very exact. It doesn't kind of shake, so there is no doctor that had a party the day before and may mess up some surgery. There's also some capsules that you can swallow, and these capsules, some of them have video, so you can get out the video signal while this capsule is going through your systems. But what Bobbins is working on, I'm not born to use these. Great, so he works on vascular robotics. So the idea is here that you have a very small robot that you launch within the vascular channel. And for example, what this could do is could then, for example, remove some blockage. It could also go to specified areas and deliver drugs at this place. So there are a lot of application areas for this. Let me see, only one, right. So what he's working with things that look like this. He actually called them size, what is it, so they can be in different sizes, but still the very same principle. And if you can do this, then you can get them to very small, small sizes. So he's using for this shape memory alloys, so you can change their form through heat. So you heat a little bit, then it takes a new form that stays, and by this he was able to get a kind of these robots kind of walking around or building a gripper that can grip something. And where does Fat IBC come into play here, right? So you want to have this kind of these very small robots going through your system, right? But then they need to, at some point, you want to communicate with them. So what they could actually do, they could kind of dock very close towards where you have your fat, and then you could communicate while they are docking here through the fat channel. You could communicate with them. This is one of these ideas. This is very far out. This is now something we hope to get to work within 5 years. Let's see if 5 years is enough, but this is one of the applications to control these very small robots. We were actually trying to find a PhD student for this, but we didn't find someone who had the kind of expertise within both the embedded software and the hardware that is needed to do this. So this is not machine learning, this is really core embedded systems and close to the hardware. Right, so this was a little bit about Fat IBC and the applications that we can do with it. So what we have shown that we have higher bandwidth. So we have actually also used Wi-Fi in phantoms, but Wi-Fi, to be honest, I'm a bit skeptical. There are some limits about how much you can heat up tissue in the human body, so we don't really know if this is within these limits. We have also shown that it works and it's probably energy efficient, but what we want to do, what is open now is kind of, can we use a technology that it calls backscatter to further reduce the energy consumption? We think that this should be possible because this works so well, and I will tell you in the next slide what this backscatter is. And one question is also, can we actually power implants using radio frequency harvesting within the body? This also requires that kind of this channel works very well to send radio frequency within that. So I just mentioned that, to be extremely energy efficient, we want to use something called backscatter. Backscatter is something I talked about here when I gave a presentation some years ago. I don't know which year, Cousin, I don't know if you recall, but I talked a while ago. So backscatter is something that is very similar to RFID in that you don't generate your own radio wave, but you use the radio wave that somebody else produces to send data. In RFID, it's typically the RFID reader that generates the data wave, but here we don't want to send ID values only. We want to send real data. So examples or how this basically works, you're getting a radio wave, and now if you want to send a 0 or the 1, if you want to send a 0, you just absorb the radio wave. If you want to send a 1, you do reflect the radio wave. So this is kind of the simplest way on how you can think that this works, this technology called backscatter. And as you know, when you can send zeros and ones, then you can do everything. So one of the problems that you have when you want to do this is that you're sending a radio wave, then somebody kind of puts their own data on top of this radio wave, but the signal that is reflected is much weaker. So if now this signal is on the same frequency as this carrier wave that you were sending, then it becomes difficult to demodulate the data. So what we've been doing, and others also have been doing, is, so we're having here a radio wave that we generate. This is the carrier wave. And then at this tags, by doing some tricks, we cannot only modulate our data, but we can also shift this radio wave a little bit. And in this way, it becomes very much easier for the receiver to decode the data that we are sending. So this is the principle of backscatter. So So here is one of our designs that we have done. This was done 5 years ago, and nobody was thinking of that we may ever think about putting this into a human body, but we believe that it's actually doable, and we have some back on the envelope calculations that show that this should be possible. So the idea was here to avoid this interference of the signal that you send from what you get by separating the carrier from the back transmission, meaning that we shift the data a little bit when we're doing it. And we also decoupled the sender and the receiver. When you have an RFID, the reader is both transmitting data and receiving the data. Here we can actually separate this. And we could operate with this at very low frequency and get some very, very long distances. And the energy consumption at the tech was 70 microwatts, which is really, really low. So typically, a very low radio has like 1 milliwatt. So here we're talking several orders of magnitude lower energy consumption. So quick summary of this backscatter. This backscatter is a way of, drastically reducing the energy consumption. You can then reduce the energy consumption so much that you can actually power your devices by energy harvesting, for example, from solar, from vibration, or you may also use other radio frequencies. So RFID always uses also radio frequencies to power a tech, but here we are actually very much independent on. We can use solar energy if we want, for example. Inside the body, of course, we cannot use solar. We may be able to use vibration if we force the person to move around all the time, right? For Italians, it may work. And so, but we think that this is actually a technology we may be able to put into the body because this communication through the fat actually works so well. And now, as I said, we've been trying to get this Internet of Things now battery-free, and what we believe is actually the combination of, if you want that to be battery-free, you need to get some energy from somewhere, right? So you can do energy harvesting, right? Solars, vibrations, whatever you have available. But there is one problem, that the energy that you get from the environment, it's coming and going. Sometimes there is some energy, sometimes there is no energy. So this means that you may have the problem which is illustrated on the next slide, right? So here you can see an illustration. On the x-axis you have time, on the y-axis here you have the voltage, here you have the operating threshold and the startup threshold. So what you can do is, you charge, typically you have a small capacitor on board, you charge it, and when you have reached the startup threshold, then you can do some work, right? You can send something, you can compute something, you can transmit a packet, but at some point you have used the energy you have stored, then you need to shut down. Then you may ramp up again when there is energy, and then you can do some work. So this is a cycle, but if you are unlucky, without any support, you would always lose your state, because if you power down and then you turn on again, if you have not saved your state, then you are where you started. So the main idea for this is that one idea is here that the main focus of something called intermittent computing is that you're actually trying to save your state on non-volatile memory so that you can survive times where you do not have any energy. And now I'm going back one slide. No, let me go to the next slide. No, and in order to get the IoT really battery-free, I think we need to combine two technologies. One is this backscatter, where you can reduce the energy consumption drastically by not generating your own radio wave, but let somebody else generate the radio wave for you. And we need to have this intermittent computing, that before we're running out of energy, we're actually saving our state on non-volatile memory, and when we're booting up again, we will reload this. And we believe that the combination of these two technology, this is the way when you want to get Internet of Things going. And this is independent if it's inside or outside the body, actually. So applications for this, we have implants, for example, where you can have some energy, but you don't need to measure very often. This, of course, doesn't work for something where you do lots of work and where you have to communicate all the time. But situations where you don't have to measure and communicate very often, these are ideal for this scenario. Also in civil engineering, for example, the inspection of dams, there you need to also do some measurements, but you don't need to do them very often. And so we have also work in this direction, but I guess in the interest of time, I will skip these slides. So there we made some evaluations if you can actually, if you can actually give sensors inside the dam enough energy, and here we used radio frequency to power them, And it turned out that this actually looks quite good, that this is possible. But what I want to talk about here now is this a work that we did recently together with researchers from Taiwan, is where we want to combine backscatter and intermittent computing to achieve a higher data yield. So what other works in the area of backscatter communication, they all assume that the carrier is always there, right? So a carrier is always there, right? And then you can send the data for transmissions. But most of these backscatter tags, they are pure transmitters, so they cannot receive anything. So they cannot receive an acknowledgement and say that, the data, to understand that the data has actually been received. So what may happen is actually now when you don't have the carrier wave always there, and when your IoT device is powered by energy from the environment, the data may actually get lost because you cannot transmit it before the carrier wave is there, or it may be lost because you're running out of energy before you can send the data. So what we were trying to do was basically combining devising an architecture that can both do that can do backscatter, but it also has some non-volatile memory, right? So that it can save some data. And we also added an RF detector, radio frequency detector, which could understand if there is a carrier wave. So the idea was kind of simple, right? We're having power, so then we are reading the data, or we're reading the sensor data, and then if we know that a carrier was there, and then we know that we have transmitted the data. But if we were not able to transmit the data because there was no carrier wave, then we are saving the state or the data on non-volatile memory. And when we have energy again, we can send it. So in this way, so this was actually a system that was built. So here you can see a backscatter tag on the left-hand side and some other things for the measurement setup. And now I can show you the graph, the results that we get. So we have here on the y-axis, we have these different technologies. We have the original tag. This tag actually had no idea if it had transmitted the data or not because it's a transmitter only. Then we have the tag that could also see if there was a carrier wave or not by having a small RF detector. And then we had a tag that could detect if there was a carrier wave or not, but it could also store the data that was not sent on non-volatile memory. And we can see that we got an increase in these experiments. On the y-axis, we have the data yield, basically the percentage of sent data that was also received. And we could see with this technology, we could increase the data yield tremendously from roughly above 20% to more than 70%. So this shows that this combination of backscatter technology and intermittent computing is actually very viable and can be useful for these very resource-constrained devices. So this brings me towards the end of the talk. What I wanted to convey for you is that, we have now a means of doing RF communication within the body. We have also means to kind of make IoT battery-free by using this concept of backscatter and intermittent computing. So what we are trying to do now is kind of, can we use this backscatter within the body? Because this RF communication inside the body works so well that also backscatter should be possible. We're also trying to see if we can use radio frequency to power some of these devices within the body also. And finally, I hope that I have convinced you that we have some interesting applications. There are some more that I can tell you about in the break if you're interested. But there are very many interesting applications from, controlling prosthesis to, trying to get micro robots into your body. So with this, I want to thank you for your attention, and I also want to thank you again for the invitation. It's always a pleasure to come here. So thank you very much.
Thanks, Thiemo, for the presentation. One application that immediately came to my mind was related to fat IBC, was that one of our colleagues is now doing some work with the marine biologists. So like in this area, in the marine biology, right? Yeah. So they are studying like dolphins and whales, yeah, kind of stuff. So they have body-worn sensors on whales, and I think definitely fat IBC should work on sea creature like that, because I believe they have a very fat layer, I would say. Yeah. So yeah, so I think that's a potential application, definitely, where this can be used. My real question is actually, what would be the protocol that you would use to communicate between these sensors?
So this is actually, so I can answer both questions, right? I mean, you mentioned water. This is this is very interesting, of course, but we have not thought so much about animals in the water, but actually humans, right? So if you go inside the water, you cannot really communicate very well, but you could actually communicate through the fat inside your body. So that would be that would definitely be possible. So it's an interesting idea with water, but also with animals. Of course, I have to admit we've done some animal experiments, so to show that this technology works. But there may also be use cases for animals, and as you say, some of these whales and so on, they have lots of fat, so this should be a very good medium to communicate if you want to do this. And if we can do something useful to conserve whales or other, animals, that would be very, very nice. Your other question was talking about protocols. We have actually, so far, I mean, we have a full protocol stack, and this is 802.15.4 based and TISH and stuff like this. So this is something we have, but it's in principle independent of what kind of protocols you're using, right? You could, I mean, Bluetooth is very much used in medical applications. So you could use Bluetooth also. That's kind of in the similar frequency range and similar output powers than 802.15.4, right? As I said, we have tried with Wi-Fi to get higher data rates. That works also, but here I'm not really sure if we're within the boundaries that we are allowed to heat up tissue, right? Because if you have higher output power, you heat up the surrounding tissue a little bit more. So that's something we still have to figure out. But in principle, we're independent of the protocol stack.
Thanks.
Hello, sir. I actually have a three-part question.
Yeah.
So you mentioned about signal leakage. And
yeah.
Why is signal leakage an important problem when it comes to RF within the body? And also, how would you define signal leakage in the case of RF, because RF transmits through a shared medium over air? So at what point does it become a leakage and not something you're actually transmitting?
Yeah, so it's a very nice question. I can start from what happens if you have no signal leakage, right? If you have no signal leakage, then nobody outside can read the packets or read the data, right? So this would mean that you do not need to encrypt any data if you want to hide the data, right? But since there is some leakage, we have to do something about this, right, to make the data private and secure, right? So that's why if there was no leakage, we would not need to do anything about encryption and that. But since there is some leakage, we have to do something about it.
So you mentioned that to make it battery, to save battery, you use signals that are already in the environment.
Yeah.
So if you're using signals that are already in the environment, these signals could be already used to transmit some data.
Yeah.
So you'd be effectively overlapping it with your own data. Aren't we taking away transmissions, maybe important transmissions to
That's also a very good question, right? So typically, I mean, to be honest, what we are doing is that we generate just a carrier wave. That's a normal sine wave, right? And then we modulate the data on it. But you can actually also use existing data, modulated data, meaning data that somebody else is sending. But then typically the data that is already there, this is much, much stronger than the little data that you modulate on top of it. So you will not have an impact on the data that is already there, unless in very specific circumstances. So the challenge is more to kind of filter out this very, very weak data on top of the already existing data. That's why we're trying to send data that is not modulated, that's just a pure sine wave, right? And one of the ideas is that you have a device somewhere that is very powerful, that doesn't have any energy constraints, and with that you can generate the data on which you modulate it. So most of these devices that are radios, they have a so-called test wave, or a test signal, and this is used for testing basically, and this is just a pure sine wave, and that you can generate also yourself and then modulate the data on top of it.
So how would the devices know that this is meant for them if you can't put a receiver tag?
So you can also, I mean, that's also a very nice question. So actually, you can, of course, decode an address, right? So you can decode the sender's address and or the receiver's address. But then there is also another technology called analog backscatter, where you don't really send, where you don't have any digital components, but you actually, you do, now this takes a bit longer, but shall we take it or shall we take it offline? I don't know.
Anything, sir, I don't mind.
Well, and so you can actually encode sensor values by shifting frequencies in different ways. So, right, a frequency shift of 1 kilohertz may mean 15 degrees. A frequency shift of 2 kilohertz might mean 20 degrees, and so on. You can do this. This is something called analog backscatter. And actually, my PhD student from Sri Lanka is working on this. That's why I mention it. And what she has actually identified that is you can then use harmonics when you generate a signal. Not only the signal that you want to have is generated, but also some signals on other frequencies. And if you're doing some tricks, you can, by looking at this other frequency, also identify who is the sender. So this is then purely analog rather than putting kind of IDs in the packets you're sending.
I have just one final question. So if you're transmitting data within FAT, are you, since you're just transmitting radio frequency waves, and you would have to use something like a directional antenna, or because you can't specify where to go to?
So you could actually, so there is one thing. One thing is that we already have a waveguide, right? So this means that the waveguide restricts where the signal is traveling, right? If you send a signal here, then it's everywhere in the room in all directions. But here the signal is confined within this FAT. But of course, if you send directional antenna, if you have directional antennas, then some things would be easier, right? For example, if you're having these tumors, it would be more, you would see this even more in the data if you have used directional antennas. So there would be some advantages of using directional antennas also.
Thank you, sir.
Yeah, thank you very much.
Thank you for the presentation, a very interesting one. I was just wondering, is it around 2.4 gig that you transmit, and is that the ideal?
So it's roughly among the ideal frequencies, but then it depends on how you define ideal, right? So for example, if you're going to higher frequencies, as I said, the antennas can be smaller, but then you're losing in distance. So 2.4 gigahertz works well, and there's all kind of existing radios and devices, so that's one reason why you could go for 2.4 gigahertz, but you could also go for higher, you know, we have also tested with 5 gigahertz, that works also, but the more practical one seems to be that 2.4 gigahertz because you get larger ranges.
Yeah, because the 2.4 has a couple of millimeter amplitude. So what would be
the wavelength is 13 centimeter roughly. Yeah.
Yeah. So what would be the like the minimum thickness of the fat layer?
So the minimum so this is very right. The smaller the fat layer is, right, the harder it gets to send the signals. So we have had very small fats, and it still works. Then it's a question of deciding the right antenna for that. And my colleague Robin, he has the expertise in designing antennas also for this very low, for these very small fat tissues.
Thank you.
Thank you.
My question is, what kind of antenna are you using for these implants? What kind of materials are you using for these implants? Because most of materials are harmful for human flesh and body.
Yeah. So there's actually one of our previous PhD students. She has designed an antenna that's very well matched for the fat layer. And the technology she uses is called a topo antenna. So this is a way of designing antenna that work well out for this. But I cannot tell you all the details, but I can point you to some papers. But they are not antennas that you buy somewhere, but they are specifically created for that.